Lecture 9.9, Ampere's Law. When studying electrostatics, if a charge distribution had a high degree of symmetry, it was easier to use Gauss's law to calculate the electric field rather than Coulomb's approach. A similar situation arises in magnetostatics. If a high degree of symmetry exists with the current density or the current distribution, excuse me, Ampere's law is a better tool to calculate the magnetic field than using the Biot-Savart law. So just to remind you about Gauss's law, let's just do a very brief review of Gauss's law, since the two are very similar. And it reads something like this. We have a flux. We have this electric flux, and the electric flux is written as E dot dA. Now the whole goal here is to integrate this over a Gaussian. And as soon as you integrate this over a Gaussian, we know that that electric field is a constant. So what that allows us to do with the flux here is that we have two conditions. We have the Gaussian surface, and then we have to worry about the dot product condition. But that allows us to pull out E and cosine theta out of the integral. So then I'm left with this integral like this. So when I'm looking at this guy is now the area of a Gaussian. And we saw that there were really three surfaces. There was a sphere, a cylinder, and a plane. So it greatly limited what was what one could use it on. And then finally, we saw that the last part of Gauss's law is that we had this enclosed charge divided by epsilon naught. So this enclosed charge told us what? That this was the enclosed charge inside a Gaussian. That's Gauss's law right there. So I want to apply the same type of thinking to Ampere's law. So now how about if we start setting up for Ampere's law? So the way we'll set up for Ampere's law is that we could say here that Ampere's law is not formulated in terms of magnetic flux. Since the flux is zero. And there's good reasons for that. And the reason why that is here is that magnetic fields form closed loops that do not leak out, and I guess stray magnetic field lines. Okay. And because of this, we could say that, in fact, Gauss's law for magnetism is del dot B is equal to zero. And that immediately tells you that the flux is zero. However, the real underpinnings of this is there are no observed magnetic monopoles in nature. That's why del dot B is equal to zero. So because magnetic fields close into themselves, once again, they form closed loops. Ampere's law is formulated by line integrals. Not flux, that follow the closed path of the magnetic field. So very similar to what we talked about in with Gauss's law, we did not derive Gauss's law. We essentially came up with some rules and then moved from there. So I'm going to do the same thing. So to derive a picture of the workings of Ampere's law, we start with a straight current carrying wire. And we have studied that multiple times already. There are two key takeaways. So the first thing, let's draw the magnetic field of a wire. So if I look at a magnetic field of a wire, you could imagine that I have, let's say that this is my current. So now what I'm going to do here is that I'm going to draw my closed loop of the magnetic field. So if I'm looking at this thing here, you could say here that here's my path. And if I follow the magnetic field around here, we see that at this point, I have a magnetic field there. Right here, I have the magnetic field as as it encircles the wire. So that's what we're seeing here. So now I'm going to write two things here. So the first thing that we want to think about is that we could say this. Magnetic fields circle around wires in a closed loop at a fixed distance from the wire. The magnetic field is constant. So this tells me that there are locations where B is equal to a constant. So in other words, if I fixed my distance from here to here, then each of these magnetic fields is then going to be a constant. That's a key point. There is a location where the magnetic field can be a constant, which is similar to a Gaussian. If I pick a Gaussian, that's a E field constant surface. So if I go to the next piece here, the next key part here, it says these circling magnetic fields enclose the current. In other words, what this is telling us here, that the path encloses the current, which we then define as I enclosed. So I could come in here and I could now say that this here is my enclosed current. So the path encloses that current. So if I move on here and get ready for from going from the Biot-Savart law to essentially Ampere's law, we could say here is that we already have calculated the magnetic field of a wire via Biot-Savart law. The goal is to manipulate the field equation to put it into a Gauss's law look alike. That is, we want to reverse engineer to get Ampere's law. So here we go. So we know that the magnetic field of a wire looks something like this. We have mu naught I divided into 2 pi r. So now this is what I want to manipulate. So if I'm going to manipulate this guy, we're then saying that I'm going to write this so that I have B of the wire, and you could see in the denominator I have 2 pi. So what does that B of the wire means? This means that B here is going to be a constant. So then the second piece here is that if I take that 2 pi r and I bring it to the other side, you'll see that I'm going to get 2 pi r, and this is the length of the path. So if I look at the other side, I'm left with one piece here, which I'm going to call mu naught I, but because we're thinking about the enclosed current in this path, this now becomes I enclosed. So in this situation, we then have the enclosed current. So effectively, that is Ampere's law. So mathematically, let's clean this up just a tiny bit. It looks like this. So we're going to see here is that if I have B of a wire, excuse me, times 2 pi r, what I'm going to need here is that in Gauss's law, there's a dot product. There's also a dot product in Ampere's law. So that dot product tells us that it's B of the wire times cosine of theta. But now, in this case, we are using a path integral over a circle. So if I rewrite this, I could then say that this guy is now a closed integral of b dot ds, and this is then equals to mu naught I enclosed. Now what we should do here is that I should come in here and I'm going to get a copy of this. Let me copy this guy here and bring it down. And then I'm going to modify this guy. And what does this picture say? So we already know that the magnetic field is a constant. We have Q enclosed, so now I just have to pick my path. So if I pick my path, I'm going to erase these. I could then say that you could see that my path in this case, because it's going in that direction like this, I could pick my path here where this is going to be my ds element. So that will be ds, and this guy will then be b. So we're going around that loop. So picture-wise, that is Ampere's law. Finally, we could write this in. Here is Ampere's law. Ampere's law, or circuital law, relates the circulation of the magnetic field around a closed loop. To the enclosed, maybe I should say electric, enclosed electric current passing through the loop. This enclosed loop is called an Amperian. I absolutely love that name. I love the way that sounds. So then if I write out Gauss's law, it's B dot ds is equal to mu naught I enclosed, and this is the integral form of Ampere's law. Now there's there's an interesting aside here, and I think we should look at it. So as an aside, we have the following thing. From vector calculus, Stokes' law allows one to rewrite the line integral into a surface integral. So mathematically, it looks something like this. So I start off with this guy. And here, just to remind you, this is a line integral that we're doing. So this is b dot ds. And so if I now go to Stokes here, this is now going to be over a surface. And then in order to make this over a surface, I have to transition this into a cross product of the B dotted with dA. But that's only half of it. That means I also have to integrate this thing also over a surface. The enclosed charge, in other words, I'm going to have to get the right units. It has to be I enclosed divided by the area dotted with the area. And so when I'm looking at this, then this leads to the differential form. Where the cross product of the magnetic field in Dal is equal to then the current density. So this is another way of stating Ampere's law. So up to this point, we could then say that Maxwell's equations, and in here, the first three, that is, in differential form are del dot E is going to be the charge density divided by epsilon naught. This is Gauss's law for electrostatics. We have del dot B equal to 0. This is Gauss's law for magnetostatics. And then finally, we have del cross B, which is equal to mu times J. This is the Biot-Savart law, or Ampere's law. So now we just have to wrap this up and sort of like give an overview of Ampere's law. So let's do that. So this is an overview of Ampere's law. So the first thing that I would do, which is the important one, is that I need to start off with Gauss's law. So I'm going to start off with an analogy before I get to Ampere's law. And the analogy says that Gauss's law starts with picking a good Gaussian surface. That is key to everything, which is only possible if the charge distribution has a high degree of symmetry. That's key. So in other words, if I have a Gaussian surface, a good Gaussian surface, that is the same as saying that we have a constant E field surface. Only then can we take the electric field out of the area integral, right? That's the only time we can do that. Ampere's law starts with picking a good Amperian loop, which is only possible if the current distribution has a high degree of symmetry. So in other words, if I have an Amperian loop, that is equivalent to stating that that is a constant B field path. And this is key because that now allows me to take the B field out of the line integral. So this becomes very important in the scheme of applying this. If you can't pick an Amperian loop where this is the case, then it's easier to use the Biot-Savart law. Okay? It's easier to use the Biot-Savart law. So now let's just finish up by talking about the Amperian loops and what's possible. So I'm going to go to the second thing. There are only two possible Amperian loops. So the first one is that circular loops are for cylindrical conductors slash wires and toroidal solenoids. So if I think about my conductor here, I could have a wire or my conductor. And what I do know about this is that this guy here, if it has a current running through it, so in this case, if I look at the current, if the current is running in this direction right here, then it's going to produce a magnetic field that encircles. So that path, my Amperian, we want to choose an Amperian, the circle to move around in a circle like that. Now the other possibility is a toroidal solenoid. And so when I look at a toroidal solenoid, you could imagine that I have a donut. So if I have this donut, then I'm going to have wires that are wrapping around this guy. And I could have as many wires as I want, depending on what we're looking at. And so what you're seeing here is that inside this toroidal solenoid, you're going to find that the path of the magnetic field is contained within this guy. And in this case, we can choose a path where that magnetic field is a constant. So to give you a sense of this, here's an actual one. Oops, wow, that's really big. Let me get this down small here. And so when I'm looking at this guy, what is my path? Well, if I use red, I think it's going to not be very bright, but you could imagine that what's contained in this guy is that I have a magnetic field that's moving around like this. That would be a toroidal solenoid. And so in this path here, we would then say that B here is a constant. So the next path that's possible is a rectangular loop. So here we have a rectangular loop or rectangular loop for the common solenoid. We haven't dealt with that yet, but a common solenoid essentially, well, let me draw a picture so you can see what I'm talking about. So you can imagine that I have this guy right here. And the key thing, it has to be longer than the opening of the bore here. So, in other words, if I see this as my opening right here, then we typically have a core. We don't have to have a core, but we typically do. So then when I look at this thing, we'll say that this guy is the thing that's actually holding the wire system in place. So this is the body of the solenoid. And so when I look at my wiring, you could imagine that I have wires that are wrapping around this guy like this. And so what we find here is that when I look at this magnetic field, this is what happens to the magnetic field. The magnetic field is running through this solenoid. And it's also coming out of this solenoid like this. So in this situation, right in here, inside, we have that B is equal to a constant. And it's only equal to a constant in there if it's much longer than the diameter of the bore. So then what we want to do here is that we now want to pick a path where the magnetic field is a constant, and then we're going to take it in such a way that I have this rectangle here. Now note that I didn't draw these fields good enough yet, but just for the sake of simplicity here, the path has to be like this here. And so if I integrate over this, then I get my loop here. So now, if I was to show you an image of this enormous solenoid here, let me bring this and make this smaller here. You could see that this is an image of this solenoid right here. And when you look at this thing, what's the path? Well, we know that inside of here, we have a magnetic field where B is equal to a constant. So then our path includes this path that looks something like this. So that's going to be our direction of the path. So because of this, we could then say the following thing. So if I look at this third thing here, the Amperian loop or the Amperian path is now integrated over these two possibilities. So if I look at this thing, the goal of Ampere's law is to pick a path where the B field can be pulled out. In other words, I'm going to get plus or minus B where I'm integrating over this path. And so that means here that I'm going to get this, and this is going to be my Amperian length. And as we will find out, it's going to look something like this. There's only two possibilities. So it's got to be plus or minus B times 2 pi r. That's got to be for circular loops. And it turns out that we're only going to integrate over one segment of the line, of the rectangle. And what we typically do is that we integrate over the line where the B field is a constant, which is inside. So this would be plus or minus B times L, and this is really over a straight line and not a box.